All right, everybody, it's time for the punchline of this week's videos and also the most important statistical result that we're going to learn about this semester, and that is called the central limit theorem. Central limit theorem is the basis of everything we do with inferential statistics for the rest of the semester. So let's get to it. Okay, so here's the idea. If samples of size n greater than 30 are drawn from any population, meaning this population can come from any sort of distribution, all we care about is that that population has mean mu and standard deviation sigma. That is true, then the sampling distribution of sample means, that's specifically of x bar, approximates a normal distribution. The greater the sample size, the better the approximation. For those of you who have done limits before, it's the limit as n goes to infinity of the distribution of x bar, and that becomes the normal distribution. This is an incredibly useful result. If the population itself is normally distributed, what is true? We've learned this already. Did you guess that it's definitely normally distributed? Then you are correct. Then the sampling distribution of any sample mean is normally distributed for any sample size n. N could be anything. And that can be proven directly, and it's a pretty cool result. But the most important result is the one about the approximation. The most important result is that for any population, no matter what the distribution is, we can take sample mean, and as long as our sample size is large enough, we can assume an approximate normal distribution for the sample mean. In either case, the sampling distribution of the sample mean has a mean equal to the population mean. So remember that, x bar mu sub x bar equals mu. And do you remember what else we learned? Sigma sub x bar. What is that one? Sigma over the square root of n, correct. So that's true, at least approximately, for any sample mean as n gets bigger. There we go. The sampling distribution of the sample means has a variance equal to 1 over n times the variance of the population, and a standard deviation equal to the population standard deviation divided by the square root of n. So there's the variance, and there's the standard error of the mean. Now, we did talk about this already a little bit, so this may be feeling just a tiny bit repetitive to you, but it's an incredibly important result. We've never given it a name before, so now you know the name is the central limit theorem. And just to make sure you've got the idea, here's our funky distribution. We don't know what's going on with this distribution, but we do know that the mean is mu, standard deviation is sigma. If that's true, then here's the distribution for the sample means. Very, very nice. Okay? Behaves very well. For a normal population distribution, we don't even care what n is. That distribution of the sample means for any n is going to be normally distributed. Now, let's see how this is useful in an actual problem. And I want to go through this problem with you, well, thinking out loud style, because I know a lot of you still do not like word problems. I don't blame you. So let's start with this word problem, parsing it out. We're on slide 20. So cellular phone bills for residents of a city have a mean of $63 and a standard deviation of 11. So what do I know so far? Well, I know the mean, mu. What is it? If you said 63, you're correct. And a standard deviation of 11, right? All right. And that's all the information in that first sentence. So I can now cross that first sentence out and stop worrying about it. All right, random samples of 100 cellular phone bills are drawn from this population, and the mean of each sample is determined. All right, random samples of size 100 means our sample size is size 100. And now I know we're talking about sample means because we've used the word mean of each sample. All right. Okay, so now I have all the information I need from that second sentence. I can draw through that, cross that out. So now I want to find the mean and the standard error of the mean of the sampling distribution. Then sketch a graph of the sampling distribution of the sample means. And it doesn't matter what this original distribution looks like, right? Because what do we know? We know as n gets big enough that the x bar is approximately normally distributed. So let's move forward. We know that our mu is 63, and therefore our mu sub x bar is 63. But for our standard error for the mean, we have to work a little harder. We know that our sigma is 11, and our sample size is 100. So we take 11 divided by the square root of 100, The square root of 100 is 10, so 11 divided by 10 is 1.1. And the last thing we're asked to do is to draw this thing. Our slide set will do it for us, but let's take a look at what we need to do. We need to have it centered at 63, and then we need to have those inflection points be one standard deviation away from the mean. Since 1.1 is our standard error of the mean, we're going to add 1.1 to get here, so we get up to 64.1 at that inflection point. And then we have to subtract 1 from 63. Let's see, that would be 61.9. And that would be there. Okay, so 64.1 here, 61.9 down there, and that should be what our distribution looks like. There it is. Well, they weren't as careful as I was, but you get the idea. All right, let's try a different problem. Again, we're going to parse this out. I'm going to think out loud. Suppose the training heart rates of all 20-year-old athletes are normally distributed. I see a number there, 20-year-old athletes, but I don't think that's really relevant. I think it's just a description of the athletes. But I do see that the training heart rates are normally distributed with a mean of 135 beats per minute and a standard deviation of 18 beats per minute. So that means my mu is going to be 135 and my sigma is going to be 18. Random samples of size 4 are drawn from this population. Okay, so that means my n is equal to 4. And the mean of each sample is determined. Find the mean and the standard error of the mean of the sampling distribution. Then sketch a graph. All right, for x bar, I'm determining this is normally distributed because the original data are normally distributed. The mean is going to be the same, 135, but I'm going to have to use these two numbers to find the standard error of the mean. It's going to be 18 divided by the square root of 4. Square root of 4 is 2, so that's going to be equal to 9. So my x bar is distributed normally with a mean of 135 and a standard deviation of 9. And that's exactly what I'm going to be told by my slides. And then they're going to graph this for me, but I know if I want to do this appropriately, I'm going to go to that inflection point and make sure that that's plus 9 up. So 135 plus 9 is 144. So 144 is exactly one standard deviation above the mean. And I'm going to subtract 9 and get 126 for one standard deviation below the mean. All right, here comes the tricky part. So we've been playing with x bar and the distribution of x bar, and that's exciting and fun. But in order to make this as useful as possible for us for our later inferential statistics, we're going to have to take that x bar and turn it into a z-score. So before, we talked about the fact that z could be equal to x, some random variable, minus its mean, divided by its standard deviation. Well, this time we're going to be working with x bar. So if we're going to create a z-statistic out of x bar, we're going to start with x bar. We can subtract that same mean because that's the same, but now instead of dividing by sigma, we have to divide by sigma divided by the square root of n, because that is the standard deviation for x bar, or the standard error of the mean. Now, if I do all of that, then this thing is, in the case where we don't know the distribution of the underlying data, it's approximately normally distributed with mean 0 and standard deviation 1. And if we know that our x's are normally distributed underneath, then it's definitely directly distributed as a normal distribution with mean 0 and standard deviation 1. So let's use that information for one more problem. The graph shows the length of time people spend driving each day. You randomly select 50 drivers ages 15 to 19. What is the probability that the mean time they spend driving each day is between these two numbers? Assume that sigma is 1.5 minutes. All right. Well, the first thing I want to realize is that there's this lovely graphic, but the only thing I care about in the graphic is the 15 to 19-year-olds, right? Everything else is extraneous information. And I've randomly selected 50 drivers, so that means my n equals 50. Furthermore, I'm given that mean time each individual person spends driving, and that mu is equal to 25. I also am given in my problem that sigma equals 1.5. So these are the three values I'm given, and now I'm told that I'm supposed to find the probability for my random sample for x bar that it is somewhere between 24.7 and 25.5. All right, so I've parsed out this problem. Let's make sure I got all the information I need. The graph shows the length of time people spend driving each day. I get that. I can cross that out. I randomly select 50 drivers aged 15 to 19. I got that information. What is the probability? The mean time that they spend driving each day is between 24.7 and 25.5, and I've got that down here, assuming that sigma equals 1.5, and I've got that original mu, and I've taken that out. So I think I've gotten all the useful information out of this word problem, and this is what I need to find. Well, let's take it bit by bit. So the first thing I want to note is that because my original mu is 25, my mean for the sample means is also 25, and that I can calculate my standard error for the mean, and it's about equal to this. Now, in order to determine this probability using our standard normal chart, I'm going to have to take my distribution of x bar and use it to create a z-score. So the original problem asked me what is the probability that my sample mean is between 24.7 and 25.5. So just like I did before, I'm going to have to do something to this inequality to turn that x bar in the middle to a z. So the first thing I'm going to do is I'm going to subtract the 25 from all three terms using my basic algebraic principles. So 24.7 minus 25 is less than x bar minus 25 is less than 25.5 minus 25. Well, I'm partway there. Now I'm going to have to divide by that standard error of the mean. I'm just going to write that in, and that's approximately 0.0212. So I'm going to divide everything by that. And since I'm running out of room, I'm going to go over here. So what does that end up looking like? Well, 24.7 minus 25 is going to be negative 0.3 divided by 0.212. And that x bar minus that mean of the sample means divided by that standard error gets turned into my z. And then I've got 25.5 minus 25, so that's going to be 0.5 divided by my 0.212. And I'm looking for that probability. Now, as soon as I use a calculator and determine the exact value for the lower term and that upper term, I'm going to have something that I can use the standard normal table to solve. So here we have the beginning part, probability of 24.7 less than x bar less than 25.5. And there's the transformations. I've got negative 1.41 on the bottom, 2.36 on the top, and I'm looking for the probability that z is between those two values. So remember how we did this? We had to go to our standard normal table, find the cumulative probability all the way up to 2.36, and subtract out the cumulative probability up to negative 1.41. Well, I'm going to let my slides do the work for me. The probability that z is less than 2.36 is 0.9909. The probability that z is less than negative 1.41 is 0.0793. I subtract one from the other, and I get the overall probability of 0.9116. So I want to remind you what this number is. I want to make sure you're interpreting this correctly. We are finding the probability that the x bar, the sample mean for that sample of 50 drivers between 15 and 19, is somewhere between 24.7 and 25.5. And the probability that we're going to find that x bar, that sample mean, somewhere between those two values is pretty high. It's about 91%. All right, let's do a few more problems related to x and x bar. An education finance corporation claims that the average credit card debts carried by undergraduates are normally distributed with a mean of 3,173 and a standard deviation of 1120. So if x equals credit card debt, then I'm saying my x is normally distributed with a mean of 3173 and a standard deviation of 1120. That's the information available in this whole section. So now I can cross that out. That's for x, which represents the debt of a single undergraduate. So now I'm being asked the question, what is the probability that a randomly selected undergraduate who is a credit card holder has a credit card balance less than $2,700? So that's the probability of a single student having a credit card balance less than $2,700. And to find that, I can use a z-statistic. I'm going to do what I did before, which is build my z from my x. So I can take x minus 3173 is less than 2,700 minus 3,173, because remember what I do to one side of my inequality I have to do to the other. And then I'm going to divide both sides by 1,120. And over here I have built my z statistic. So that's the probability that z is less than negative 0.42. So this is the probability I'm going to have to find using the standard normal table. Following the solution given in the slides, we're asked to find the probability associated with a certain value of the random variable x. There we have our original normal distribution with the mean of 3,173. We are looking for this probability, the probability that x is less than 2,700. We do our transformation, and we find that that's equivalent to the probability that z is less than negative 0.42. We can use our standard normal table to look that up, and we discover that that value is 0.3372. So the probability that a randomly selected undergraduate student with a credit card has a debt of less than $2,700 is about 33.72%. All right, here's the second part of that problem. Now instead of asking me for the probability that x is less than 2,700, we're being asked about x bar, and specifically x bar for n equals 25 undergraduates. So we're being asked what is the probability that x bar is less than 2,700. And I want you to remember our mean, mu, of x was 3,143. So that's going to also be our mean of x bar. Our sigma was 1,120. Well, we're going to have to calculate the sigma for x bar. If you remember, that's the sigma divided by the square root of n. So that's going to be 1,120 divided by the square root of 25, which is going to be equal to 224. So this probability that x bar is less than 2,700, I want to build this out so that I get a z on the left-hand side. So I'm going to take x bar minus 3,143 less than 2,700 minus 3,143. I'm going to divide both sides by 224 because that's the standard error of the mean. So what I've created on the left-hand side is a z. On the right-hand side, I need to calculate out what that value is. And through math magic, I can tell you that it's negative 2.11. So following the solution given by our slides, we're asked to find the probability associated with the sample mean. We're going to find the mean of the sample means. We're going to find the standard error of the mean, just like we just did using our pen instead of our slides. And then we're going to have to do that transformation and discover that the probability that x bar is less than 2,700 is equivalent to the probability that z is less than negative 2.11. We then go to our standard normal table, discover that that probability is 0.0174. And so that's it. That's our probability that x bar is less than 2,700 for a sample of size 25. Now, do you recall what the similar probability was for x? It was about 0.3372, if I remember correctly. So there's about a 34% chance that an undergraduate will have a balance less than 2,700, but there's only about a 2% chance that the mean of a sample of 25 said students will have a balance less than 2,700. So that makes that an unusual event, that the sample mean would come up to be less than 2,700, even though it's not that unusual for an individual's credit card debt to come up less than 2,700. Now, this idea is going to come back when we start to learn about things called confidence intervals and hypothesis testing. So I want you to keep that in the back of your mind. It is possible that this sample is unusual, or it is possible that the corporation's claim that the mean is 3,173 is incorrect. All right, so that's the end of our material for this week. Whew, there was a lot of material, a lot to cover. Please feel free to look at these videos more than one time. You might want to watch them once, wait a day, watch them again, because this material is difficult. And most students have a difficult time learning this stuff because it's unlike anything you've seen before in your other classwork. So if this is feeling mysterious and confusing, you are not alone. I want you to give the homework a try. The more you practice with these ideas, the less foreign and alien they will seem. Good luck this week, and I will see you soon.